through and out of CRESP. And hopefully some of the things that you see excite you and inspire you to continue your research. As always, if you have any talks that you'd like to see or any research that you'd like to present, feel free to contact any of us on the CRESP committee, and we'll make sure to find a time slot for you. But today, we have the pleasure of having Dr. Xinyue Wang, who is a postdoctoral scholar with the Department of CE at Vanderbilt University. She received a PhD in environmental engineering from Vanderbilt University in 2022. Today, her research focuses on the geochemistry and leaching assessment of fly ash at disposal sites by combining laboratory leaching characterizations, large-scale field studies, and geochemical speciation modeling. She currently works on the integration of leach testing and hydrological modeling for long-term leaching assessment. I'll let you take the floor from now, and we look forward to hearing your talk.
Okay, so everybody can hear me, right? I will share my screen. So, good afternoon, everyone. My name is Xinyue Wang, and today is a great pleasure to have the opportunity to present. And as introduced earlier, I'm currently a postdoc at Vanderbilt University, and I work with Dr. Coulson's research group. So I just got my PhD degree last September, and today what I'm going to talk about is part of my dissertation research. So basically, I have been working on the geochemical assessment of leaching from coal ash at the disposal facilities. And today I'm going to talk about the lessons we learned from the research project. And this project is funded by both APRI and the CRESP program. So I have been working on this program with several colleagues, and each of them provided valuable inputs from the different perspectives. So my research focuses on the coal ash, which is a byproduct from the coal combustion. The coal ash is one of the largest types of industry waste in the US. And in the past 10 years, on average, about 50% of the produced coal ash are disposed at on-site facilities, including the impoundments and the landfills. So the impoundments are the wet disposal sites for the coal ash, where the ash is mixed with water and then piped into a steaming pond, like shown in the left. And the landfills are the dry disposal sites for coal ash. So currently, for most of those disposal sites, there are no liners in the bottom, which means that the constituents within those coal ash has the potential to be leached into the environment and then cause cancer. According to an EPA report, several constituents of potential cancer have been identified in the coal ash, such as arsenic, boron, chromium, molybdenum, and selenium. And we can see most of those constituents are oxyanions forming constituents. In the figure, we can see within a typical pH range between pH 8 and pH 12 in a disposal sites, those oxyanions shown in this dashed blue curve typically has higher concentrations than the cations, therefore is of more concern. The disposal of the coal ash at those on-site facilities receives increasing attention from the public, partly because of several coal ash spills happened in the past years. I think some of you may heard of it. For example, the most famous one was happened at Kinston, Tennessee in 2008. In this coal ash spill, about 1 billion gallons of coal ash was spilled into the surrounding river due to a dike failure, and it cost a lot of money for the cleanup program. And the workers working on the cleanup program also reported health issues. And also there was another one happened in Adams, North Carolina in 2014. So to evaluate the potential environmental impacts of those coal ash disposal sites, it's important to understand the leaching behavior of constituents, because it basically can tell you how much of the constituents can be released under the field conditions. For the leaching assessment, currently the most widely used methodology is the leaching test methods. Those leaching test methods can estimate the leachability of constituents. However, there are several challenges to directly apply those test methods for the field leaching assessment. The first challenge is that in the field, the geochemical conditions can be quite different from that in the lab test condition. For example, the oxidation reduction potential or the redox condition is an important variable to control the leaching of constituents. But this variable is not easily to be duplicated in a lab test environment. So the lab test conducted at the altered redox condition will have the problem to represent what's going on in the field. And second, currently most of those tests are carried out on those fresh ash directly collected from those electrostatic hoppers, which have not been disposed at those field sites. But actually, when you put those fresh ash in a field site, the weathering of ash can happen, and this will change the chemical composition of ash and therefore affect the leaching of constituents. Therefore, for the leaching assessment of constituents in the field, it's important to focus on those field material and focus on the leaching under the actual field conditions. Based on this background, overall, this project aims to improve the understanding of leaching of constituents under the field conditions. And specifically here, we will assess the impacts of those environmental conditions and site configurations on the oxyanion leaching under the field conditions. And this will be achieved through two field case studies on two actual disposal sites, including a closed impoundment and an active coal ash management unit. For these two focused field sites, first, the field environmental conditions will be characterized by the pore water and subsurface gas sampling. And then we will collect the ash samples from each of the sites and use them in the leaching and solid phase characterizations. And finally, we will use the geochemical spatial modeling to simulate the leaching in the field and help us to understand the mechanisms controlling the leaching in the field. So here are the introduction of the two field sites. So the site 1 is a coal ash impoundment, which was closed at our field sampling. Actually, it just 1 month prior to our field sampling. So before the site closure, the ash in the impoundment was dewatered, but still precipitated with water. And then for the site closure, a vegetation cap was used to close the site. And for the Site 2 is an active coal ash management unit. It generally consists of 3 layers, like a sandwich. First, in the bottom, there is a historic coal ash impoundment. And then on the top, there is a dry managed coal ash landfill. And between the 2 layers, there is also a thin layer of bottom ash used as the capillary break. Actually, the Site 2 is much larger than Site 1, which you can't tell just looking at the figure. So the surface area of the Site 2 is almost 4 times of the Site 1. And also the Site 2 is much deeper than the Site 1. So on these two sites, we did a lot of sampling activities. One of them is to collect the ash from each of these sites. To do that, we selected several locations on each of these sites and then drill boreholes into the ground to collect the samples beneath the surface. At Site 1, we selected 3 borehole locations. We can see here from VB1 to VB3, which covers this triangle pond area. And at Site 2, we selected 4 borehole locations from VC1 to VC4, covering the entire management unit. Since Site 2 is much larger, so we selected 4 locations rather than 3 borehole locations. And then at each of those borehole locations, the bulk ash samples are collected for the leaching characterizations. So basically, we used a split spoon sampler to collect the samples from the different depths. And we can see the top picture is an example of the samples we collected. And then in addition to those individual split spoon samples, we also used a thin wall Shelby tube to collect the Osterberg course for hydraulic property test at University of Virginia. So these field cores are the intact cores with minimal disturbance on the hydraulic properties of the ash. And we can see for each of the core samples collected, the samples are extruded from the sampler and then carted for the test for the hydraulic properties. After the collection of those ash, we also installed the sampling wells for the pore water and subsurface gas monitoring. For the pore water sampling, we can see here we installed a pore water screen well, which shows in the black color into the saturated ash layer. And for the gas sampling, we installed a gas sampling tube in this red color into the vapor zone or the unsaturated ash layer. And at site 2, we can see we have several gas sampling tubes into different depths into the ground. Because the site 2 has a much thicker dry landfill, this provides an opportunity to understand what's the gas composition variations with the depths. So after the installation of those sampling wells, we did monthly sampling of the pore water and the subsurface gas. The pore water was measured for some basic chemical properties and concentrations of constituents, and the subsurface gas was measured for contents of oxygen, CO2, methane, ammonia, and hydrogen sulfide using a portable meter as shown on the right figure. So at each of these sites, the monthly sampling lasted for about 1 year. Then another major part in our study is to do the leaching test on the samples collected from the field. And one of the tests we have done is the extraction test on those individual samples collected from the different depths. First, in the field, we set up an field extraction test immediately after the sample retrieval in the field. And this test aims to recover the pore water from those coal ash samples before it's further exposed to air, so the redox conditions of the original sample can be preserved as much as possible. And in addition, we also did a lab extraction test on those samples which have been exposed to air during the field sampling and lab handling. And then we can compare the results between the lab extraction test and the field extraction test to see how the handling of the samples during the sampling and the lab handling will affect the leaching of constituents. In addition to those tests on the individual split spoon samples, we also created some ash composites. So these ash composites are created by homogenizing portions of samples from different depths into the ground. And then those ash composites were used in the pH-dependent leaching test following the EPA method 1313. So basically, this leaching test evaluates how the leaching responds to changes in pH ranging from pH 2 to pH 13. And then we will use these test results to calibrate our geochemical speciation model. So this model will be used to do the leaching predictions in the field conditions. And here is the basic idea of the geochemical speciation modeling. So the geochemical speciation modeling will be performed to simulate the pH-dependent leaching test results on the ash composites. And in the model, we will include a long list of constituents from the major, minor, and trace constituents. And what we got from this model is a virtual definition of the material. So this virtual definition consists of several components. First, it contains the content of each constituent that can participate in the leaching reactions. And second, we will develop a mineral reaction set accounting for the dissolution and precipitation reactions in the system. And finally, we will have a description of the adsorption surfaces for the oxyanions. Then we can use the virtual material to simulate the partitioning of the constituents under the field conditions using the field pH range, field liquid to solid ratio condition, and the field redox conditions according to what we observed from those field case studies. So this geochemical speciation modeling can help us to identify what controlling mechanisms for those oxyanion leaching under the field conditions. And here, then I will show you the results from each of the site. And the first is for the site 1. Here are some basic chemical properties of the site 1 field ash. So the site 1 field ash is featured with low calcium content, which is about only 1% in weight, but it also has high amount of iron. And we also compared the available content of the trace constituents in those field ash to the range of available content in the fresh ash, which has not been disposed in a disposal site. So the term available content is a little similar to the total content, but it's not exactly the same. The available content is the maximum leachability of a constituents that can participate in a reaction. So it's typically lower than the total content and is only a fraction of the total content. So basically we observed here is that in the site 1 field ash, several constituents showed quite low available content in the field ash compared to the fresh ash, such as for boron, molybdenum, and selenium. The reason for that is that the sluicing process of the ash in the field with water during the past years before the site closure has removed a lot of soluble fractions of those oxyanions from the solid phase into the liquid phase. But then where did these dissolved constituents go? We don't have a quite clear answer for that. And what we found here is also that the site 1 field ash is relatively enriched in arsenic compared to the other ash, and arsenic is a very important constituent of potential concern in the coal ash. From the pore water sampling, it tells us that the pore water pH environment is near neutral with pH between 7 and 8. And the range of PE conditions suggests that the field environment is alexic to suboxic. But when the samples are collected for the field extraction and lab extraction test, we found that the PE gradually increased because of the sample oxidation. And this PE increase also accompanied by a pH decrease. And this is likely because of the hydrogen produced by the oxidation reaction. So this comparison tells us that the sample oxidation can quickly happen during the field sampling and the lab testing process. For example, even though in the field extractions, we try to set up the test in the field as soon as possible of the sample retrieval, but still you will see an increase in the PE because of the sample oxidation compared to the original redox state of the samples within a field site. In addition to the pore water sampling, the subsurface gas composition can also help us to have an idea of what the field geochemical conditions look like. At site 1, what surprises us is that the high concentrations of methane are recorded at all the borehole locations. So in these figures, the methane concentrations are indicated in those light purple color. So for example, we can see at VB2, the methane concentrations higher than 5% are consistently recorded at across the 1 year of sampling. So in the figure, the methane concentrations are indicated at 5%, but actually the 5% is the upper calibration limit of our meter. So actually the concentrations can be higher than 5%, even though it's showed 5% here. And in addition, we also detected hydrogen sulfide at some borehole locations. The detection of this methane and hydrogen sulfide showing that there is methanogenesis and sulfate reduction reactions happening in the field, and these reactions are indicators of a strong reducing environment at the site 1, and this is not expected before our field sampling. So then, what's the impacts of the field geochemical conditions on leaching of constituents? First, let's look at the results for arsenic. In these figures, the arsenic concentrations in pore water are indicated in those red spheres. We can see at VB1 and VB2, the pore water arsenic concentrations can be as high as 4 milligrams per liter, but this concentration decreased substantially in the lab extraction test and field extraction test. So please remember, as we said earlier, in the pore water, the environment is most reducing, but the redox conditions got more oxidized in the field extraction and lab extraction test. And we can see here, the lab extraction test with the most oxidized environment has the least arsenic concentrations. So this basically tells us that the difference in the redox conditions between the lab and field environment is somehow impacting the leaching of arsenic. And later we will use the geochemical speciation modeling to help us understand the underlying mechanisms. Compared to the arsenic, the results for selenium are quite different. So in the pore water, we actually detected quite low selenium concentrations, which are below the detection limit. But as the environment become more oxidized in the field and lab extraction test, we can see the selenium concentrations gradually increased. And this is consistent across all the borehole locations. And in addition to selenium, the vanadium and antimony, these two constituents, also showed very consistent results. So this tells us that the different redox conditions between the lab and field is affecting the leaching of multiple constituents. And these constituents are all redox sensitive constituents. Then we use the geochemical speciation modeling to help us understand the reasons cause such difference. So here we can see the geochemical speciation modeling results are showing in those dashed lines. And this is the simulated concentrations of arsenic as a function of PE, starting from PE of 5 to PE around minus H. And this PE range stands for a redox environment starting from suboxic to strongly reducing condition. So we can see that the arsenic simulated arsenic concentrations is a strong function of the PE of the system. And this is accompanied by by different valence state change of the arsenic. First, we can see when the PE decreased to about decreased from about 5 to minus 2, the arsenic 5 is reduced into arsenic 3. And the arsenic 5 and arsenic 3 have different adsorption abilities on the edge surface. And this difference in adsorption ability will result in different leachate concentrations of arsenic. And then when the PE further decreased to about minus 6, which is under a very strongly reducing condition, the arsenic 3 will be precipitated with a sulfide mineral. And this precipitation of the mineral will cause the arsenic concentrations to decrease. And under this PE condition, we can also observe the methanogenesis and the sulfate reduction. That's what we are seeing in the field. So this tells us that the arsenic leaching is quite sensitive to the PE condition or the redox condition of the system. So that's why we are seeing the different leaching behavior of arsenic in the field and in the lab test condition. For selenium, the controlling mechanisms are quite different. So for selenium, when the environment is suboxic, the major selenium species is selenium 4 adsorbed to the edge surface. But then when the environment become more reducing, when the PE decreased to about 2, the selenium-4 is reduced into selenium-0 and form a mineral elemental selenium. And then when the PE further decreased to about -1, the selenium-0 will be reduced into selenite and then form a precipitation with iron and form this iron selenite mineral. So this selenium-0 and iron selenite mineral are in insoluble phases, and this will cause the selenium concentrations in the pore water quite low. So that's why at this site, we saw very low selenium concentrations in the pore water, but the concentration increased in the lab leaching test environment. So what we just saying is that is the results for the redox sensitive constituents. But actually, there are also some constituents for which their leaching behavior was relatively independent of the redox condition, such as the boron and molybdenum. For example, the boron shown here has the similar total released mass in the pore water and in the field and lab extraction test, despite of the different redox environment. This is because that for the boron, which is highly soluble constituents, the leaching is primarily controlled by the available content in the solid. Therefore, both the lab and field extraction test can approximate the leaching behavior in the field and not affected by the redox condition of the system. And then we will have show you the results for the site 2. So the site 2 field edge has moderate calcium content, about 5%, which is different from the low calcium content in the site 1 edge. And this difference will also cause the different leaching behavior of constituents. And we will see some examples later. And according to the XRD analysis, we detected the calcite and ettringite, the two minerals in the site 2 field ash. And these two minerals previously have not been detected in the fresh ash. So the calcite, I think we are familiar, is a weathering product from the reaction between calcium hydroxide and the CO2 in an alkaline environment. And the ettringite is a product from the hydration of ash and also has been reported as a weathering product in the alkaline ash. So the detection of these weathering products will also have the impacts on leaching of trace constituents, and we will also talk about it later. According to the pore water measurement, the pH environment at site 2 is alkaline, which has a pH range between pH 10 and pH 11, and this is different from the site 1, which has a near neutral pH condition. And the range of PE suggests that the site 2 environment is suboxic and is less reducing as the site 1, which is strongly reducing. And this suboxic field environment is also consistent with the gas compositions. So as shown in the bottom figure, for example, here, the three adjacent bars are the three gas compositions from different depths into the ground, and the depths increased from the left to the right. This blue bar is the oxygen concentration. So we can see the oxygen concentrations decreased with depths and then stabilized at less than 1% at the deepest sampling location. And unlike the site 1, the methane and CO2 are barely detected at site 2. So this means that the site 2 environment is not as reducing as site 1, and the environment is suboxic. The reason to cause such difference in the redox condition is because of the different pH environment. At site 2, the field pH environment is alkaline, so the pH is above 10. And this alkaline pH environment is not favorable for those microbial reduction activity, which is necessary to generate a reducing environment. But at site 1, which has a near neutral pH environment, is more suitable for those microbial activity. So this tells us that the field conditions at site 2 is quite different from the site 1. And then in terms of the leaching of constituents, we also found that the results at site 2 is quite different from site 1. For example, for arsenic, here as shown in the left bottom figure, the pore water arsenic concentrations in these blue squares are well approximated by the light blue curve, which is the lab leaching test at a low liquid to solid ratio, and also approximated by the field extraction test in the triangle green color. And this is also the same for the other constituents like boron and vanadium. So this result is quite different from what we seen at site 1. If you remember at site 1, we see quite different concentrations of arsenic in the pore water and in the leaching test. And this is not seen here. According to the geochemical special modeling, it told us that at site 2 field condition for the three constituents, the leaching of the arsenic, boron, and vanadium under the field conditions is controlled by solubility of minerals, and the redox variations between the lab and field condition is not in the range to trigger the change in valence state of those species. So both the lab and field extraction test can well reflect the pore water concentrations of these constituents without the influence of the different redox condition. We can see that the geochemical speciation modeling results in these dashed lines matched well with the experiment data in the lab test, and also matched well with the pore water measured concentrations. According to those phase diagram, the arsenic concentrations in the pore water are controlled by a calcium arsenate mineral, but this mineral was not present in the site 1 field ash because the site 1 field ash has a much lower calcium content and will not form such a mineral phase. And for boron, the boron is incorporated into a weathering product, the carbonate solid solution. And this carbonate solid solution controls the solubility of boron under the field condition. And for vanadium, the concentrations in pore water are controlled by a calcium vanadate phase and an etrangite solid solution. So the etrangite solid solution is also a weathering product from the ash disposal in the field site. Unlike the three constituents we just seen that without the impacts from the redox conditions, actually we do observe the impacts of redox conditions on leaching of chromium and selenium at the site 2. And I will show you the chromium results, for example, here. So for chromium, we measured quite low concentration in the pore water, which are below the detection limit. But then the concentrations increased substantially in the lab leaching test. And the reason for that is that the geochemical speciation modeling suggests that under the field pore water conditions, the chromium concentrations are controlled by a chromium 3 oxide mineral. So this chromium 3 oxide mineral is quite insoluble and will resulted in very low concentrations of chromium in the field suboxic condition. But then when the samples got oxidized from suboxic to oxic condition in the lab, the chromium 3 will be oxidized into chromium 6. And this chromium 6 is much more soluble than chromium 3, and therefore will result in higher concentrations in the leachate compared to in the pore water. And this bottom figure shows us that how sensitive the chromium leaching to the PE change of the system. So when the PE increased from about 2 to 7, the chromium concentration increased by over 2 orders of magnitude. And this is consistent with the chromium concentration increase from in pore water to in the field extraction test, and further increased in the lab extraction test. So in summary, we found that the two sites has quite different field conditions. First, for the field pH condition, the site 1 is near neutral, while the site 2 is much more alkaline. And this difference in the pH condition also resulted in different field redox condition. The site 1 with a near neutral pH condition is strongly reducing, but the site 2 is less reducing and is suboxic. And also the leaching controlling mechanisms for constituents in a field site can be quite different between these two sites because of different field conditions and the different chemical compositions of ash. For example, at site 1 with for the site 1 ash with quite low calcium content, the adsorption, desorption, and solubility of a sulfide mineral is important to control the pore water concentrations. But at site 2, for the ash with a higher calcium content, the solubility of a calcium arsenate phase is important to control the solubility of arsenic in pore water. And also at site 2, due to the formation of several weathering products like the carbolate solid solution and the ethangite, it affects the leaching of multiple constituents such as the boron and the vanadium, but this has not been observed at site 1. So finally, we have some take-home messages from this study. Overall, we found that the field geochemical conditions varied by the chemical composition of the ash and also the site configurations. So here, the two field studies we focused on cover two typical field conditions for coash disposal sites. The first one is a strongly reducing condition, and the second one is a suboxic condition. So the key factors to result in the different field redox condition is suggested as a field pH environment. For those disposal sites with near neutral pH condition at the time of site closure, we think that a reducing field environment may be common. But for those disposal sites with alkaline ash, a suboxic field environment is expected to maintain for substantially long time because of the long time scheme to transform from an initial alkaline condition to a near neutral pH environment. And finally, when we use the nab leaching test results to estimate the field leaching, the results should be carefully interpreted in the context of the site-specific conditions and the individual constituent behavior. So that's all for my presentation today, and I hope everyone can find it useful. Thank you.
Thank you very much for that enlightened talk. At this point, I'd like to open up the floor for any questions, if anyone has them right at the starting gate. Yeah, go ahead.
You done? Yeah. Thank you, Xinyue, for your nice presentation. So you have mentioned that the leaching result, it depends on the site condition. And you have two sites. One side come for wet disposal, and the other side things are covered by the dry disposal, as we have discussed some differences to the site conditions and affect the leaching results. Can you hear me?
Yes, I think my connection is not stable, so I actually can't hear clearly what you said.
Okay, so I mean, you have mentioned in the first slide we have two different type of disposal of coal ash. One that we can wet disposal it or we can dry disposal it. Will this affect the different disposal method will affect the condition of your disposal site and affect the leaching result or not?
Now, can you repeat the last sentence? I just lost it. Yeah.
Yes. I mean, the different disposal method will this affect your site condition and your leaching result or not for wet disposal and dry disposal?
Actually, I think the major influence of the wet disposal and dry disposal on the leaching is mainly about the hydrologic conditions. Because for the wet disposal, you will have a higher water discharge, but for the landfill, the site is quite dry and you will have a less discharge from the site. So if you are thinking about the long term, this will affect like how much cumulative mass of the constituents can be released as a function of time. For example, like those impoundments with more wet conditions, you will see like more release in a specific time interval compared to those dry conditions. But actually, if you look at those equilibrium conditions as we studied here, it doesn't impact too much about the results.
Sounds good. Thank you.
Any further questions?
Can I ask a question? So
Yeah, go ahead,
Yeah,
Nick.
sure.
yeah, I've seen you a nice presentation. So I work with you on a lot of this work, and I know the leach access is the one you're using for the compare with the batch reactions. So I just curious, what's the differences between the leach access and the mean tech? Because I used that a lot before. So yeah, can you just briefly explain like that? So,
Actually, it's not the leach XS.
Uh-huh.
It's the orchestra. So leach
Orchestra, okay,
XS,
yeah.
leach XS is only like a data management software to help us like manage a large data set, like help us to plot the data. It's actually the orchestra, which is the modeling platform. So I think regarding the equilibrium calibration, the mean tech and the orchestra have quite similar capabilities. Like they can also both do those like calculations with the mineral reaction set and also the adsorption surfaces. But what the MinTag cannot do is the transport process. But this can be done in the orchestras. And in orchestra, you can, since we work with the developer, so we have the flexibility to change like basically whatever we want to do to the system. Like, but for the mean tag, it's like already a well-developed software. So it has like limited capabilities if you want to like change the system, which is more complex compared to the simple system.
Okay. Thank you.
Can I ask one more question, Xinyue?
Yeah, sure.
Yeah, I think so. I'm not quite sure what the scope that I understand for your study, but I believe your research kind of find a better way to manage the coax that has been deposited in landfill for many decades, right? It is one of your scope. So can you provide some?
Actually, we can. What we can do is to provide some like consultants to those companies. Like for example, currently, I just give you an example. The disposal of those coal ash so those coal ash has been already put in a disposal site, and now people are worrying about in the long term, will those constituents be leached into the environment and they cause the environmental pollution, and then this cause the problem to those facilities. Like there will be like a lawsuit about like if you put the ash there, will this cause the environmental pollution? And what we will do is using those scientific data to tell them like how much constituents can be leached, and in the field, like in the long term, how much like how we can estimate for them like the source term of the release of constituents, but we cannot tell them exactly will this cause the environmental pollution. So we are providing them the basic scientific data. And so yes, like an example application.
So do you have, based on your result, do you have any recommendation to deal with those old ash ponds? Because I know EPA, the regular from EPA kind of shifted a little bit for the recent years, right? So
yeah. Actually, that is also a motivation from this research, because the EPA is changing its management for the old disposal sites. Actually, from our side, we can like we cannot do much to change the policy. Like they already have their policies for those old impoundments. They have to they are no longer, they can be no longer be operated for those active coash impoundments. They have to like close those sites. And also for those another way for them to manage those coash impoundment is to like drag the ash out and then put a liner in the bottom and then put the ash back. So that's two ways for manage the coash impoundments now. We cannot do much to change this policy. We can only tell them like if the impoundment is there, will like how the constituents can be leached from this impoundment and as a source term.
Okay, got it. Yeah. Thank you.
Do we have any further questions? All right, well, I will thank you once again for the enlightening talk today, Dr. Wang. And I invite anyone who would also like to present or has someone that they'd like to see present in the future, please reach out to us at any time. Otherwise, I wish all of you a very happy Friday and keep on sciencing.
Thank you.
Thank you.
Well, thank you much.
Yes, thank you.